Okay, so now look at this next problem for finding shear force and bending moment diagram. Again, just to remember, and I'm drilling this into your head so that it's easy for you to follow, and that is that the slope of SFD equal to BMD, equals load, distributed load, slope of BMD equal to SFD, and jumps in shear force diagram equals concentrated load, upwards positive, jumps in bending moment diagram equal to concentration moment, counterclockwise negative, clockwise positive. So remember that. So now we are ready. As usual, we draw first our axes, x and y. Then step 2, find reaction forces. In our case, we already did that, and then we can draw FBD with all forces. And as we said before, draw a large free body diagram because it will help you. So I'm going to draw another one of those long ones so that you can see. Oops. So that you can see. So I'm going to draw. Okay. So we have already calculated this. So I'm going to write it down 2.5 kilonewtons from this reaction. That's that. And then that one is 7.5. That turns out to be that guy. And then we have this distributed load up to half the beam. Okay, this is 2 kilonewton per meter. And then there is a concentrated moment, and that's going 50 kilonewton meter. Notice it's counterclockwise. Sorry, so notice that it is clockwise, so it is going to jump up. Okay, so that's our free body diagram. So now we're going to draw our shear force diagram, and I'm going to mark these 2 points, and I'm going to draw a straight line through, and then I'm going to mark this point, I'm going to mark this point, I'm going to mark this point, and we are ready. So we are going to jump up by 2.5 kilonewtons. So I'm going to say, okay, so we are going to use that. It's about 7.5 kilonewtons, right? So we are going to use roughly each one is 1. So 1, 2, 2.5. So that's my initial jump. And then, as usual, it's always convenient to find the areas. This area will be 2 times 5, that's 10 kilonewtons. So I know that this is going to be down from here by 10. So 2.5 minus 10 is minus 7.5. That is 1, 2, 3, 4, 5, 6, 7, 7.5. So it's going to be a straight line that goes like this. And then it's going to go flat. So 7.5 goes all the way down and jumps up by 7.5. So this one is 7.5. This total height 10 is this area, right? So now we have introduced a new point, that point, which turns out to be, if I want to find out, so notice that this is 2.5, and I want to come down. So from 2.5, the slope is 2 units. So it's actually a fairly easy calculation to see that this is 1.25 units. Okay, and the area under this curve, A1 is actually plus 2.5 times 1.5 divided by 2, which turns out to be 1.56. Okay, and the area here is minus 12.5. If you compute it, it will turn out to be minus 12.5. No, sorry, it's more like 14.06. This area. Okay, if you compute it roughly, I'm just giving you a rough idea for these numbers. Okay, so that's our basic dimensions, and this area is 7.5 times 5. It is 37.5. So we need these areas, and I'm putting negative. Areas that are below the x-axis are negative. Areas that are above the x-axis are positive. So we'll use that information. So now we are ready to draw the bending moment diagram. So again, make yourself plenty of space. So I'm going to start out here at 0. And you notice, first thing is, again, it's a parabola. This whole thing is one giant parabola. You can see that, right? Initial slope is 2.5. Final slope is minus 7.5. So it starts out initially at a slope of 2.5, and it ends up here with a slope of minus 7.5. You can see that the parabola is going to look like that. Okay, that's going to be the shape of the parabola. So it's going to reach a maximum. The question is, where does it reach a maximum? It's at this point, because there the slope is 0. So 0 slope, that's the maximum point. So it's going to look like a parabola which is downwards. Why is it downwards? Can you see the distributed load is saying down, point down. So the parabola is going to point downwards, the same way as the distributed load. So it's going to look like that. I'm terrible at drawing these things. By the way, the location of this is way down here at minus. So it starts out at 0. It goes up, and then it will come down, and it turns out that this is the height to which it goes. So let's mark these points. At this point, its height will be 1.56. That's this number. So this area will be this height, and that's 1.56. And then this area will be this. Subtract that area from here, and you will get minus 12.5. That's equal to 1.56 minus 14.06. That's this area minus that area. So what will happen is, my parabola looks, and then very steep. So this slope is actually 7.5, negative 7.5. This slope is positive 2.5. This location is where the slope is 0, and its height is given by this area. That area is here. Then after that, that much area I subtract. Now comes the interesting part. If I try to complete this by saying, okay, from now on, from here on, the slope is minus 7.5, and you go like this, that would be wrong. Why is that wrong? Because you forgot this concentrated load. So what this concentrated load is going to do is jump this up by 50. It's going to go way out here. I told you, right? This bending moment diagram will jump up and down a lot. So there, it's going to go way up there. It's going to jump up by 50. And so this height is 37.5. That height is 12.5. Together they make up the jump of 50. And then from there it's a nice straight line. So it goes 0. So compared to these numbers, this is huge. Of course, you can see that my drawing is not to scale because I didn't give enough space. If I actually draw the drawing to scale, it will completely, the bending moment diagram will be huge. So I want you to understand that bending moment diagram, you have to be careful. This jump comes from the concentrated moment. So as usual, the main thing is if you cross the x-axis with your shear force, there will be a maximum or minimum. Okay, so you have to mark that point and figure out how high it is, and it all depends upon this area. So this area is this height, then subtract out that area and you'll get this location, then add this area after you jump and all that and you'll get that one. Okay, so it's kind of a tricky issue, so I hope you got this one.